Okay, this screencast is about the integrated rate law. First, though, I want to start with one of these problems, that initial rate method, where we can figure out the order of a reaction based on some experimental data. So I wanted to show you this one because in this set of data, we have one reactant that does not have two identical concentrations. So I thought this one would be a very good practice for you guys to go through and see if you can determine the rate law where it's not all nice and neat, where something does cancel out. So I'm first going to start with my basic rate law expression. It's going to be BF3 to the X and ammonia to the Y. And that's what we're going to try and figure out. I can see that if I compare reaction 1 and reaction 2, the amount of BF3 stays constant. And so that would allow me to solve for Y. And that's what I'm going to do first, because I don't have the same concentration for any of these with ammonia. So I'm going to compare reaction 1 to reaction 2. So reaction 1, and I'm going to compare it by dividing. And so I'm going to plug this into that rate law expression. This is 0.2130 equals K times 0.250 to the X times 0.250 to the Y. And then underneath that, I'm going to do reaction 2, which is 0.1065 equals K times 0.250 to the X times 0.125 to the Y. All right, so in comparison, our rate constant is going to be the same. These two cancel out. And so that makes it a little bit easier to solve for our exponent. And what we end up with here is we get 2 equals 2 to the Y. And that lets us know that Y is equal to 1. So I know that this guy right here is now to the first, or is first order with respect to ammonia. Okay, so now what we're going to do is we're going to actually have to use that bit of information that we just found, the order of ammonia, in order to compare two more reactions. So let's compare reaction 2 and reaction 3. We do want to kind of mix that up and not use the same two reactions here. So let's compare reaction 2 and reaction 3 in the same sort of way. So we're going to compare reaction 2 to reaction 3. And so plugging it into that basic rate law expression, I get 0.1065 equals K times 0.250 to the X times 0.250, and not to the Y. We know it's to the first power. So that's no longer a variable, and that's going to be really important as we solve this. So reaction 3 is 0.0682 equals K, and this is 0.250. Oops, no, it's not. In reaction 3, that is 0.200 to the X times 0.1 to the first power. Now, in this go, the only thing that's going to cancel out really is going to be K. But that's okay. We can divide the rest of them, and it will be just fine. So what I end up here is 1.56 equals, this divided by this ends up being 1.25 to the X, and this ends up being 1.25 when I divide those two, because they're just to the first power. Well, then I'm going to need to solve for X, so I'm going to divide by 1.25 on both sides. 1.25, and that cancels there. And so then I end up with 1.25 equals 1.25 to the X, And so we know that x is equal to 1 in this case as well. And so we can now update it. And so our rate law expression would look like this. It is first order with respect to BF3, and it is first order with respect to NH3, and it is second order overall. All right. Let's get rid of these guys. Okay, so let's talk about the integrated rate law. It expresses the reaction concentration as a function of time. So you'll end up with questions like, what will the concentration be at a later time? How long until the final concentration reaches this molarity? So form of the equation depends on the order of the rate law. So it depends on that differential. So we've got changes in concentration over changes in time, and we need to see whether a reaction is zero order, first order, or second order. Those are the ones that we're going to be working with. There are other orders for reactions, but we're going to limit it here in this class to 0, first, and second order, and usually with just a single reactant. So first order reactions, we have a reaction here, and we have found that the rate equals K times the concentration of dinitrogen pentoxide, and it is first order with respect to that nitrogen pentoxide. And we've determined that experimentally. So we know that it is a first order reaction. If the concentration doubles of that dinitrogen pentoxide, then the reaction rate also doubles. If we integrate this equation with respect to time, we get the integrated rate law. And what that's going to look like for this particular reaction is that it's going to be the natural log of that dinitrogen pentoxide. This is going to be its concentration at time t. That equals negative K, and that is our reaction constant, times the time it takes for it to get to that concentration, plus the natural log of the initial concentration of that dinitrogen pentoxide. All right, so ln is the natural log, and when we see this little sub-zero right here, that means its initial concentration. It is the concentration at time equal to 0. And that is its final concentration, or its concentration at whatever temperature or time we're looking at. All right, so if we determine that a reaction is first order, and again, it would be to the first power. A lot of times we don't have to write that. So R equals K times the concentration of A. So that's its general form. The integrated rate law form looks like this, and A is our reactant. If we look at this in the form of a line, we have y equals mx plus b. And we can make some generalizations, and we can also have an idea of what the graph of this will look like, and that can help us determine the order of a reaction in case we didn't know already. So if we look at this integrated rate law in the form of a line, that line-intercept form, m x plus b. We can see that the natural log of our final concentration would be our y, and we can see that time would be our x. Our slope would be related to the rate constant. Negative slope is going to be our rate constant, and b is going to be that starting concentration of whatever reactant we have. So if we graph the natural log of our concentration versus time, we're going to get a straight line if it is first order. And that's going to be really important for us to remember going forward. A lot of times they're going to ask you to solve for time instead of concentration. And so you would just rearrange that equation. And this is actually the form that the integrated rate law for first order is given to you in on the reference sheets. Okay, so the half-life is the time required to reach half the original concentration if the reaction is first order. Radioactive decay is a great example of first order half-life, and as far as the AP curriculum goes, you only have to know first order half-life. The time to reach half the original concentration does not depend on the starting concentration. It's always just cut in half. The equation for this, and it is given to you on your reference tables, my half-life time, which is T1 half, is equal to 0.693 divided by K. So this becomes a really, really easy way to find K for a first order reaction if you're given the half-life. And we'll look at some problems where we have to use that. Second order reaction, it's R equals K times the concentration of our reactant. In this case, we're just going to use A as our reactant to the second power. The integrated rate law for second order reactions looks like this. And so you can see it's very similar to the one for first order, except instead of natural log of A, we've got 1 over A. And it's done that way for the initial concentration as well. The other thing I want you to notice is that we have a positive K here. And that means if we put this into our slope-intercept form, we get, this is our Y and equals M. Our slope is our rate constant times our X value. I wrote T again. And this is our X, and this is our V right here. So you can see that the graph of 1 over the concentration of A versus time, it is a positive slope, and that does give us our rate constant K, if we can find that slope there. So a straight line if 1 over the concentration A versus time is graphed, and that can help you prove that something is second order. Zero order, zeroth order too, they'll have it that way. In this case, A is to the 0 power, and anything to the 0 power is equal to 1. So really, our rate equals our rate constant. It does not depend, it does not change on our with concentration. And in this case, the concentration of A versus time is a straight line. If you see conditions where the concentration of A versus time is a straight line, then that proves it's going to be 0 order. You will notice that our rate constant is equal to the negative slope of that line. All right. So, 0 order rate law most often when reactions happens on a surface because the surface area stays constant. And so this applies to enzyme chemistry, surface catalysts, and we're going to look at a lot of those as we go further into this chapter. So I referred to this as I was going through here. What's given on the reference sheet, they give you first order integrated rate law, and they give you second order integrated rate law. You have to know which one is which. And they give you the half-life for first order. And those are all the calculations that you are going to have, are going to be asked to do in AP Chemistry. Okay. So here's a little summary. We had lots of information on lots of different slides. So I thought it would be helpful to kind of put things together here. Our just basic rate law. This is going to be R equals K times the concentration of A to the 0 power. Or we could just write R equals K. For first order, R equals K concentration of A to that first power. Again, we don't have to put that 1 there. And for second order, R equals K, concentration of A to the second power. Then we have our integrated rate laws. So we can use these right off of the ones on the reference tables. So for first order, it's natural log of A equals negative KT plus the natural log of the initial concentration of A. For second order, it is 1 over the concentration of A equals KT plus 1 over the initial concentration of my reactant. Half-life, T1/2 equals 0.693 divided by K for first order, and that's the only one you have to know how to use. Plot needed for a straight line. For zero order, it is the concentration of my reactant versus time. For first order, it's the natural log of A versus time. And for second order, it's 1 over the concentration of A versus time. If you get a straight line when you graph any of these, that helps you prove that it is zero order, first order, or second order. And then the relationship of the rate constant, so that's K, to the slope of that straight line that we're talking about here in this row. So for this one, the slope or negative slope equals K, and for this one, slope equals K. Okay, so that's just to put all this information on one page so you can kind of keep first order separate from second order and how you think about these. But we will need to memorize what to use where. Okay, so let's look at some practice. The order of this reaction. So here we have 3 different graphs. We've taken some data, the concentration of A over time, and then we've expressed it in 3 different graphs. We've done the concentration of A versus time, the natural log of A versus time, and 1 over the concentration of A versus time. And we're looking for which one of these gives us a straight line, and it is this one. So we would say that the reaction is zero order. And so this would be R equals K would be its rate law expression. We've done the same sort of thing in the next reaction. Here we've got C4H6 yielding products. In these graphs, I have the concentration of that substance versus time. I have the natural log versus time, and I have 1 over the concentration versus time. And then I'm looking to see which one gives me a straight line, and that would be this one right here. Looks like the straightest line that I have. And so we would say that 1 over the concentration of our reactants versus time, that means this reaction is second order, and the rate law expression would be C4H6 to the second power. And we can tell all of this just by examining the graphs. In this one, we're back to A, and again, we've taken the concentration of A over time, and then we've expressed it in 2 different graphs. We have the concentration versus time, the natural log of the concentration, and a 1 over the concentration versus time. I'm looking for that straight line, and the thing that gives me the straightest line is this one right here. So natural log versus natural log of A versus time. This is a first order reaction, and so R equals K, concentration of A to the first power, or we can just leave it looking like that. Often you will get questions like this on that AP exam.